Okay, great. So actually, I was already sitting on the plane together with another speaker of the conference, ready to take off to California, but then our flight was suddenly canceled. So that's very disappointing that I won't get to meet you in person this time, so hopefully next time. So today I'll be talking about crystallization dynamos, which I've been working together with Jim, Adela, and Ilaria. So let's begin. So as you all heard yesterday, as white dwarfs cool down, at some point their interiors begin to crystallize. They start forming these crystal solid cores that gradually grow in size from the inside out as the white dwarf continues to cool down. Can everyone see my pointer, by the way? Okay, good. So in the case of a CO white dwarf, for example, as we've heard, this crystal core is enriched in oxygen. And this means that the crystallization process leaves behind a carbon-rich liquid, which is now lighter than the surrounding ambient C&O mixture. And because of this, it will buoyantly rise upwards, generating convection. And this convective motion, combined with the white dwarf's spin around its axis, can generate a large-scale and strong magnetic field through a convective dynamo. And this is the focus of this talk. So these crystallization dynamos were first suggested by Jordi Searle et al. In this very nice pioneering paper several years ago. And in order to actually calculate the convective velocity that powers the magnetic field, one needs to know delta rho, the density contrast between these liquid elements and the surrounding white dwarf material. Once you know this density contrast, delta rho, you can easily calculate the buoyant acceleration upwards and therefore the convective velocities and hopefully the magnetic fields. But we think that the story is slightly more complicated. So imagine one of these fluid elements of size L. And now the key point here is that as soon as this element begins to crystallize, at the very onset of crystallization, it will already develop some very small density contrast compared to its environment. So it will gently start to buoyantly rise upwards. And this movement upwards might actually not give enough time for this entire element to fully crystallize. So this element might not actually have enough time to reach this full density contrast that was assumed in previous works. To put it in other words, there's a competition here. A competition between the rate of crystallization, the rate at which this crystallization front advances outwards, and the rate at which these elements rise upwards, which is their convective velocities. And the actual density contrast is reduced by this factor, by the ratio of these two velocities. And it's important to understand that crystallization is a very slow process. As you know, it takes giga years to crystallize the entire white dwarf. So this R dot over here is a very small velocity, very small number. So the density contrast is actually much smaller than previously thought. And this means that convection is much slower than what previously thought. And as you can appreciate from these arguments, the critical quantity that we need to calculate is the size of these buoyant elements, if you like, the mixing length in the problem. And this mixing length is limited by several other length scales that are all given here as a fraction of the total size of the white dwarf. So this is the y-axis. The bottom x-axis here is the white dwarf's effective temperature, and the top x-axis is the time since the onset of crystallization. So over time, white dwarfs evolve from the right to the left in this diagram. And the first limit to the size of these elements is simply the size of the underlying crystal core R, which is marked here by this dashed blue line. So initially at high temperatures, there's no crystallization. Then at some point around this temperature, a crystal core begins to form, and it gradually grows from the inside out until the entire C&O layer becomes crystallized, until the crystallization front reaches the hydrogen and helium envelope. So that's one limitation. Another limitation is simply the classical mixing length scale of the potential scale height just above this crystal core. This is given by the dotted red line. And finally, these elements are limited by the overall size of the convection zone. And the convection zone is limited from the outside by this R out, marked by this magenta line over here. So you can see that at late times, convection reaches all the way to the hydrogen and helium envelope. But at earlier times, convection actually stops in the middle of the C and O layer, and that's because of gradients of C2O that stabilize against convection. So factoring all of these length scales together, we finally get the mixing length size, which is given by the solid black line over here. So initially it rises, it follows the growing size of the core, then it gradually decays, and finally it goes to zero as the entire C and O layer becomes crystallized. Okay, so now we know how to calculate the mixing length, so we know how to calculate the convective velocity. Now we would like to know how to translate this convective motion, or if you want, the kinetic energy in convective eddies, into a magnetic energy density. So what is the magnetic field? And the answer to this in convective dynamos depends critically on the interplay, on the ratio between two numbers, two timescales. So one timescale is simply P, the spin of the white dwarf around this axis, and the second timescale is T convection. This is the convective turnover time of these convective eddies. And remember that we find here that convection is very, very slow. And this actually means that practically all observed white dwarfs are in the fast rotating regime, where they spin much faster than the convection. And in this regime, one very popular scaling relation is simply equipartition between these two energy densities. But actually, there are some recent 3D MHD simulations, as well as some very good analytical arguments that would claim that in this fast rotating regime, magnetic fields can actually reach super equipartition values. So the magnetic field is further enhanced beyond equipartition by this ratio of two timescales. So you can see that the faster the white dwarf spins, the stronger the magnetic field. And we tested both of these possible dynamo scaling laws over here. So here we plot the magnetic field in megagauss as a function of the effective temperature. And the bottom lines here, the black lines at the bottom, these assume equipartition. And this would give us fields of order 0.1 megagauss. But if you now assume the super equipartition scaling, this one, then you can see that we can get stronger fields as a function of rotation. So these are the blue and the red lines. You can get to several megagauss and even up to about 100 megagauss, depending on how fast the white dwarf spins. The dashed lines here are for 0.8 solar mass white dwarf, and the solid lines are for 0.6 solar mass white dwarf. And the qualitative behavior here is similar. So initially at high temperatures, there's no crystallization. Then at some temperature, either here or here, depending on the mass of the white dwarf, crystallization begins, and the dynamo quickly kicks in. It then reaches a maximal. This is when the convection reaches the helium envelope. And then at the end, the dynamo shuts off and the magnetic field dies off. This is when the entire C and O layer becomes crystallized. Okay, so this is the theory. Now we would like to actually compare these two observations to see which observed white dwarfs could actually be explained by such a crystallization dynamo. So here we plot the magnetic field strength as a function of the spin period. And this dashed black line over here, this is the maximum field predicted by our theory. And again, you can see that the faster the white dwarf spins, which means going to the left here, means a stronger maximal magnetic field. And we've populated this plot with observed white dwarfs for which we have both the spin and the magnetic field measurements. And we've color-coded them, either red or blue. So this, for each white dwarf, depending on its mass, we can check whether its temperature is too hot to actually have started crystallizing. So these are red. or whether they're actually cool enough to be covalently crystallizing. So these are blue. And you can see from this plot that crystallization dynamos can explain only some magnetic white dwarfs. So many magnetic white dwarfs are either too hot to be crystallizing, so they're red, or even if they're blue, many white dwarfs are simply way above our predicted maximum for their spin period. So crystallization dynamos seem to explain only the blue markers that are below, or maybe just slightly above this black dashed line. And this is only about 30% of this very particular and probably very biased sample. And now I want to turn your attention to several interesting groups in this sample. So one group are these blue star markers, these three. So these are these very interesting binary emitting white dwarfs that we recently discovered. So these are white dwarfs that exhibit binary emission lines. And very interestingly, all of these cluster at very similar temperatures, around 7,500 Kelvin. And this was actually one of the motivations for this work, one of the original motivations. We wanted to see whether crystallization, which also occurs more or less at these temperatures, can explain this clustering. And you can see that actually the measured fields are not that far off from our maximum, but we actually find it very difficult or somewhat difficult to explain the clustering using crystallization. So we're still not sure about these ones. Another interesting group are these magenta diamonds over here. And these are not actually single white dwarfs. All the rest here are single white dwarfs. But the magenta diamonds over here, these are binary white dwarfs. These are intermediate polars. So these are all magnetic white dwarfs in CVs. And presumably these will span up to the fast rotation by mass accretion from a donor. And you can see that all of these are actually more or less consistent with a crystallization dynamo. Okay, so I think it's more or less about time to summarize the talk. So it was argued that several years ago that crystallization inside white dwarfs could generate strong magnetic fields through a convective dynamo. And the strength of this field depends critically on the interplay, on the ratio between convection and rotation. We find in this work that convection is much slower than previously thought. And this means that magnetic fields are potentially much stronger than we thought. And when comparing these fields to the observations, we find that they can explain some, but definitely not all, single magnetic white dwarfs. But this mechanism does seem very promising and may, in fact, possibly explain maybe even all magnetic white dwarfs in CVs. Okay, so just finish off by saying that this was a rather theoretical talk. The comparison to observations here was very basic, but there are several other papers, including by people in the audience, that applied this mechanism more systematically, more comprehensively, to both observe single magnetic white dwarfs and to binary magnetic white dwarfs. So I encourage you to take a look at these papers as well. And with this, I will thank you, and let's discuss this. Thanks.
Okay. Thank you. Questions? Ingrid?
Hi, Ingrid Pellisol here. Thanks for the very nice talk. Do I understand correctly that in your model, as soon as crystallization kicks in, you have a magnetic field? We don't have to wait until the core is crystallized to a certain percentage or something?
Yes and no. I mean, we don't have, so basically the magnetic field more or less follows the length scale, and this at early times follows the size of the crystal core. So even if you have a rather small crystal core, you will have some magnetic field, but it will be smaller. The slope here does depend on the rate at which the crystal core grows. So you reach the maximum field, or close to the maximum, only when you do have a sizable core. But we might have a delay because magnetic fields might also take some time to diffuse outwards. And the diffusion time, I haven't shown it, but the diffusion time initially is very long. And the diffusion time becomes short only once convection reaches the helium layer. So if the only means for magnetic field to get out is by diffusion, then you have to wait basically until this point, which corresponds to this point, and this is when I don't know, a sizable fraction of the white dwarf has already crystallized.
Perfect, thank you.
Evan?
Hi, Sivan, great talk. This is Evan Bauer. I'm wondering, does the dynamo require some differential rotation, and does that sort of constrain like where it's operating in the interior?
Yes, a good question. So actually, there are many kinds of dynamos that rely on different kinds of motions. So as I understand it, the classical convective dynamo doesn't require any differential motion. It only requires convection plus rotation. So even a solid body rotation should do. So this is different than other dynamos that we think that operate in other conditions where you do need some differential rotation. At least to my understanding.
Thanks.
Okay, McCormick?
So it looks like you need fast rotation, and we saw that white dwarfs, rotate about a day or so typically. So do you need mergers to explain the rotation rates for the single white dwarfs? And if so, how do you know if it's from, if the dynamo comes from the merger event or from this? Is there a way to tell?
Yeah, that's an excellent question. I actually thought about this also earlier. So you do need some rotation to get strong magnetic fields. So one way to get fast rotation is not by a merger, but by mass accretion from a companion. So this is what I tried to mention regarding these intermediate polars. Regarding the single magnetic white dwarfs, that's a good question. So if they gather by merger, perhaps the magnetic fields will form earlier in the merger itself. But if you understand crystallization dynamos, you could also just form a magnetic field during the crystallization. It's a good question. Obviously, some of these white dwarfs, if you believe the theory, the magnetic fields will probably formed by a merger because they're much stronger than the crystallization field. But now, what about these guys? Their fields are consistent. But the rotation rates might indicate a merger as well. I'm not sure how to differentiate between the two.
Any more questions? Ken?
Hey, Sivan, it's Ken.
Hey, Ken.
Hi. So yesterday we heard about some other ways to change the composition in the structure of the white dwarfs. So neon 22 sedimentation and distillation and iron 56 fractionation. Have you thought about what that would do to this mechanism?
So my only thoughts were how they affect the rate of crystallization, because at the end the strength of the magnetic field depends most critically on the rate at which the crystallized core glows. So there would be this effect, but this is rather small because all the parallels here are quite weak. Whether or not the composition stability itself will change because we now have sedimentation, which might change the mean molecular weight. No, I haven't thought about it yet, but that's an interesting question. Because at the end, the convection depends on the mean molecular weight. And if now the composition changes, then the onset of convection and where convection exactly will reach might change. So it's all a function of the mean molecular weight. That's the only quantity you need to know, I think, to zero for order to understand the convection. But I haven't thought about it more than that.
Yeah, and maybe there's some fluid motions associated with those processes too. So that could be interesting to discuss.
Okay, thanks. I think about that. Thanks.
Okay, we thank our speaker again. Thank you, Sivan.
Thanks.